start off.
Okay, so let me share my screen. Can everyone see my presentation?
Yes, thank you.
Okay, perfect. So hi everyone, my name is Adriadna Murguia-Berthier. I'm part of the TCAN collaboration, just so that you know that this is a TCAN talk. And thank you everyone for coming. So today I'll discuss the post-merger simulations and how we study the debris from the merger and also the effects of a tabulated equation of state plus neutrinos. So why do we care about a tabulated equation of state plus neutrinos? So this is, I'm going to say some, okay, I'm going to give a very brief introduction just so that everyone is on the same page about what is going on in the post-merger phase of the binary neutron star merger. So here we have a black hole and we're going to have an accretion disk that form after the merger. So let's talk about the physics. So photons are going to be trapped everywhere in the flow just because of the very high temperatures and densities. The outer regions of the disk are going to be very thick and very radiatively inefficient, and they're going to be composed of alpha particles. But as we go into inner regions, there's going to be recombination, well, dissociation of alpha particles into free nucleons, or recombination if you go to the other side. And that is going to release some energy. There's actually going to be a peak in the enthalpy, and that is going to drive a powerful wind and also thicken the disk as we go in the outer regions. So this is a very important effect. Now, another thing that's going to happen is as we go inner and inner into the disk, the density is going to increase, the temperature is also going to increase, and at some point, so beta reactions are going to be ignited, so we're going to create neutrinos. So here's going to be this region where neutrinos are transparent and they are going to serve as the main cooling agent of the disk. So they're going to take a lot of the energy away and they're going to thin the disk. Now, as we go into deeper regions, the neutrinos are going to become opaque. And at some point, depending on if the mass accretion rates are high enough, they're going to become trapped, just as Jonah mentioned. So, I mean, Jonah already put all the different things that could happen. I'm just going to put some interesting reactions, which are the ones that we actually consider for the code. So the neutrino reactions that I'm going to talk about are the charge beta process, the plasmon decay, and the electron-positron pair annihilation. So not surprisingly, since this is a very neutron-rich material, in the charge beta process, this is the reaction that's going to be the most dominant. Therefore, we're going to create more antineutrinos in this event. Now, this here, which is the inverse of the charge beta process, it's going to be the opacity source. Again, since the material is very neutron-rich, this reaction right here is the one that's going to be dominant. So therefore, we're going to have that neutrinos are actually going to be the most opaque ones. So we're going to have something like this, just as a summary. This is a plot of the radius, and this is the mass accretion rate. So these are the outer regions of the disk, and let's just choose a random mass accretion rate and see what happens to the disk. So in the outer regions, again, we have lots of alpha particles. At some point, they dissociate. There's a wind, and we're going to have free nucleons and protons, well, neutrons and protons. At some point, again, the density is going to be high enough so that it ignites the beta process, and we have neutrinos. So here, neutrinos are going to be the main cooling agent in the disk. And at some point, they're going to become first opaque to neutrinos, and then the disk is going to become opaque to antineutrinos. Now, again, at very high accretion rates, we can have the neutrinos trapped, but this is not the case for our simulation. So in summary, what we have right here is that we need to consider, is there a question, Bini? Well, we're going to need to consider what happens with when the alpha particles dissociate. And in order to do that, we're going to need a realistic equation of state. On the other hand, we also need to consider what happens when neutrinos cool the disk. So we need some kind of neutrino transport or approximate neutrino transport, which is what we used, which is called the Lipid scheme, in this case in particular. Now, why do we actually care about all of this? So in order to understand the disk and its final outcome, we're going to need simulations that include general relativity, of course, because we have a black hole right here. We're going to need MHD because we have very strong magnetic fields. We're going to need also a nice way in which to consider the neutrinos. We're also going to need a realistic equation of state to take care of the alpha recombination. So we're going to need all of that. And the problem is that the final composition of all of this ejecta, or all of these processes. So when you have the disk, there's going to be MHD turbulence that drives material from the disk onto the black hole and drives this really powerful outflow. And this really powerful outflow, the composition is still uncertain. And it's because it really, really depends on the electron fraction and on what happens with the neutrinos, on what happens with the equation of state. So there is a lot of debate on what is happening in this ejecta and what is the final composition. So we need to, everyone work and try to get what is the final composition, and we need to all work together. And of course, this is very important because as material falls from the disk to the black hole, some material that becomes unbound, it will have very high speeds. There's going to be nucleosynthesis of very high elements. And the problem, again, is that we still don't know exactly what the final composition is. And the differences in this final composition are going to matter a lot in what we see in the very end and what the observers tell us that they see. So if we create lanthanides, for example, we're going to have a very red transient. And on the other hand, if we don't have lanthanides, we're going to have a very blue transient that's going to peak a little bit before the red transient. So we need this information in order to tell our observer friends when and where to look in the sky after, for example, LIGO tells us that they saw a binary neutron star merger. So this is extremely important. And what we did is we tried to, well, we're going to use HARM 3D. And here I'm going to present how we added a nuclear equation of state or a tabulated equation of state and the effects of neutrinos in order to try to play our part in this debate. And this is again part of the TCAN collaboration. So HARM is a really nice code. I'm sure everyone here has probably used and knows about HARM. So it solves the equations of GRMHD. It's fully parallelized. It's very well tested. It evolves the electron fraction. Well, this is new to this version. And the nice thing is that it has arbitrary coordinate systems. So it's much less diffusive than a Cartesian grid, for example. It has lots of analysis tools and it's extremely versatile. And in particular, new to this version, which is HARM 3D plus Nuke, we already have tabulated equations of state and added a neutrino leakage scheme. So I'm not going to go into a lot of details about what we did. And you can, of course, check this paper, which has been newly accepted. So I'm making a little bit of promotion here. And of course, you can ask me. But we added several conserved to primitive variables. And we tested this by getting the relative error after the conversion from conserved variables to primitive variables. So we set some primitives and then converted them and then got the relative error, comparing several routines that do this conversion. So here what I'm showing is a grade of the temperature and the density. And this is the relative error for all the routines that HARM 3D plus Nuke now has. So one thing that I should clarify is that this 3D routine, which is a very nice one, it's the fastest one and it's the most accurate one, but it's the least robust. So this is actually our primary solver now. And then after it, if this one fails, it goes into a 2D routine, which is a little bit slower and a little bit less accurate. And then it goes to a safe guess, to a dogleg method, and finally it goes to a Paulin-Swellen method. But these are a little bit more robust, well, more robust than the 3D ones. And this is the most robust one. So, well, as you can see, one of the things is that we clearly have a very nice relative error. So this has all been tested out and we're good with that. Now, one of the things that we learned about the equation of state in particular, because we also tested this with a Fishbone-Moncrief disk, and we wanted, well, that is isentropic, and it has the enthalpy of that you can get it for Fishbone-Moncrief. But we wanted to say a little bit about what lessons we learned. So one of the lessons is that in the tabulated equations of state, the enthalpy can actually be less than 1 in some of the tables, depending on the reference mass. And in Fishbone-Moncrief, the boundaries of the disk are set to when the enthalpy is 1. So we needed to actually take care of that and make the boundaries a little bit different with an enthalpy of like 0.99 something. So now the boundaries are correct and the torus is actually in equilibrium. Another thing that we learned is the atmospheric treatment, because the atmosphere around the torus can actually be dense enough so that it can collapse. So what we need to solve this is have the density decrease as a power law and also set the atmospheric density very, very low. And this helps the material because the material outside the torus is now going to be eating very, very slow or fall very, very slow into the black hole. And that helps a lot with the stability, just like some lessons. Now, in order to simulate the neutrinos, we use what is called a leakage scheme. So we considered all of these reactions, and we have the rates from Ruffert et al. And we also are basing on these other papers. And again, we consider this 3 reactions and scattering, and this absorption is our main opacity source. So in here, what we did is we added a cooling or heating rate to the energy equation, and we also added an absorption emission rate to the number conservation equation. What's really nice is that these effective rates are in interpolation between the optically thin and thick regime. So we're actually considering both regimes relatively, well, it's approximate, but it's still a really good approximation. And we use spectrally averaged quantities. So what do we do with the optical depth? So this is very interesting because we're using a local approach instead of a global approach. And it's the one described in Nielsen and also Dan Siegel's paper. So what we do in general is just we center at a cell and we try to see what is the minimum opacity to get to all of the other neighbors. And we try to then get what is the minimum opacity and do one iteration, which would tell the neutrino to go into a specific neighbor. And then we do a lot of iterations, which is essentially tracing a path of the neutrino to actually leave the system. So we tested this with a sphere. Well, in this case, it's a 2D simulation, so it's a disk that is in the center, it's optically thick, and in the outer regions, it's optically thin. And what the neutrino should do is just escape like this. And we're going to try to simulate that. So this is showing the optical depth as a function of radius for this sphere. This right here is the analytical estimate. And these are some estimates from our simulations using different iterations. So if we use one iteration, we actually get a pretty bad result because we only say the neutrino like, okay, only go to one neighbor. But if we do more and more iterations, we're basically telling the neutrino what to do. And we actually get a really nice reproduction of the analytical result. So we created a convergence criterion. And in here, this dashed line shows the analytical solution. And the other lines represent for different resolutions what we get for the optical depth, again, for this sphere. And what you can see is that we get a pretty nice and very robust optical depth, which is really nice. So what we do is we take a first guess that's 20 times the number of maximum cells, and this says to the neutrino what to do. And then after it, at every time step, we calculate the optical depth with our convergence criterion, and we only need 1 or 2 iterations to converge to the solution, which is really nice. So again, it's a very local approach, which is also nice. Now, as for the leakage scheme and how we tested this is based on Jonah's paper. If we take an optically thin gas that has constant density and constant temperature and just let it evolve, we can semi-analytically calculate what's going to happen and we can compare it to simulations. So here I'm showing the temperature and the electron fraction of the para processes, both with neutrinos and antineutrinos, and basically the end results. And what's nice is that, of course, we reproduce the leakage scheme. Well, what should happen? So having tested this code, now we can apply it to a magnetized torus. So here I'm going to show some movies of a magnetized torus that has a realistic equation of state. It has neutrino cooling, it is isentropic, and it has a mass of around 0.03 solar masses, which is just trying to simulate the post-merger torus. So these are very zoomed in movies, and I'll just put play. So one of the things that you can immediately notice is that there's this really nice wind that, of course, comes from the alpha recombination, because alpha recombination occurs in the outer regions of the disk. Then you can also see that in here, the disk is getting thinner, and this is where neutrino cooling is dominant. Again, as Jonah mentioned, this disk is going to be relatively neutron rich, and this confirms what Dan Siegel and Brian Metzger found of a self-regulating mechanism, which is where neutrino cooling and the MHD heating, MHD turbulence heating balances out, and you get this really nice equilibrium of the YE. So you have this reservoir of neutron-rich material, which is really, really nice. Now I'm going to show the same movies, but just zoomed out. I don't know if you can see it, but this right here is the torus, and this right here is the torus. So I'm just going to show how the outflow expands. And again, you see this right here is the wind that's unbound by the alpha recombination, and you see this like really nice, very neutron-rich material wind that is evolving. Now, additionally, what we also did was calculated at this thickness and the mass accretion rate, and this is what I'm showing right here. This is averaged in different times. So yellow is the latest thickness and the latest mass accretion rate. So here, let's focus a little bit on the thickness of the disk. So right here is more or less where the alpha recombination starts to happen. So as you can notice right here, you get a thickening of the disk just due to the alpha particles being, well, the nucleons recombining into alpha particles. And you also get this part right here where the neutrino cooling dominates. So this is neutrino cooling, well, this is thinned by neutrino cooling, and this is thickened, let's say, by the alpha recombination. And on the other hand, we can see from the mass accretion rate plot that right here is more or less when the alpha particle recombined, and you see this really nice wind, which is shown by the negative mass accretion. And this is just where the neutrino cooling dominates. So here I'm also showing the neutrino luminosity and the mass accretion rate as a function of time. What I want you to notice from these plots is that the mass accretion, the luminosity of the neutrinos traces the mass accretion rate relatively well, which is not surprising because we expect more neutrinos to be created due to magnetic heating from the magnetic stresses. And therefore the emission should then remain relatively stable, as you can see. And I mean, we evolved it to 114 milliseconds, but of course the main idea is to evolve it for hopefully a second. And this is using realistic initial conditions that are going to be handed off from Illinois GRMHD, which you already heard about. And tomorrow you're going to hear about how we're going to do the handoff. So our conclusions is that we're ready for the handoff. We already have the code that's harm3D plus nuke. It already has tracer particles also that Joseph might talk a little bit about. And we're ready, it's already been tested. So we're ready for the handoff, which is going to be really, really cool. And I hope that you all can see the papers coming out hopefully in a couple of months. And it'll be really, really interesting. And of course, we perform simulations on a magnetized torus just to test the code and study the impact of neutrinos on recombination to alpha particles. So thank you very much. And if you have any questions, just feel free to ask me.
Thank you very much, Ari. See some applause in here. Very nice talk. Is there a quick question anyone would like to pose? I had a very silly question, but I don't want to take up valuable question time for other people, especially since I'm supposed to know. But I'm going to ask you very quickly anyway, because I don't see something. Just going back, kind of moving to before you started talking about neutrinos, you're talking about the different con to prim results, and you mentioned that the 3D is both more accurate and faster than the other approaches. And
yes.
Just I naively think 3D sounds like more work than 2D.
Yeah, no, that's actually a great question. The main issue is that the 2D routines need to do a temperature inversion. So that is so you need to do another Newton-Raphson within the Newton-Raphson. So that takes a lot of time. And you need to do lots of Newton-Raphson iterations within Newton-Raphson iterations. So that's the bottleneck of the 2D routines.
Okay.
The temperature inversion.
Okay, thank you. There's a text question from Jonah in the chat. Really fantastic talk. Do you have a sense for how much of the outflow is magnetically driven rather than thermally?
Yes, so that is a great question. And let me just say one thing. So our MRI is not the best because there was a bug with the MRI. So we're periodic in, if I remember correctly, it's pi/8. So the MRI is not the best. So we're not very well resolving it, but we're definitely going to resolve it for the TCAN handoff. So there we're going to be able to answer this better, I guess. But yeah, that's a very interesting question.
Okay, thank you very much. And I made it worse despite my best intentions. We're a little bit behind, but thank you very much for great